Thank you for the opportunity. I thank the organizers for the late start today. Much appreciated. I'd also like to acknowledge the contribution of my co-authors. This is a team effort with equal contributions from everyone involved. And it's a contribution of the Pages Working Group on Quaternary Interglacials. Okay. Shown here is the summer solstice insolation 65 degrees north over the last million years, and the Lysikian Ramo benthic delta 018 stack, and as a broad measure of ice volume. And denoted here with red arrows is what Eric Wolf showed yesterday, is the definition of interglacials from the past interglacials working group of Pages. A definition that is, an interglacial is defined as an interval within which ice volume in the northern hemisphere was similar to today, i.e. with very little ice outside Greenland. And we all know that there's not a simple answer to this. There's some strong insolation peaks, like at stage 6E, with very little change in ice volume. And conversely, there's some very moderate insolation peaks with very strong response in stage 11. So George Philander said a few days ago that this is not a question worth asking. We remain undeterred, and we still ask whether the onset of interglacials over the course of the Quaternary can be predicted from simple combinations of astronomical parameters without any knowledge of any climate data. Okay, first, we need to define the population of Quaternary interglacials. And we use the Lysikian Ramo curve again for the entire Quaternary because we simply do not have an independent sea level curve for the entire period. And an interglacial is defined as a period when its isotopic minimum exceeds a threshold here. We also defined. So I should say that we all know the isotope stratigraphy has been divided into even and odd number stages, but there has not been a systematic attempt for the entire Quaternary to define complete deglaciations, i.e. interglacials, from incomplete deglaciations, interstadials. And so in an interstadial, if it doesn't exceed that threshold, we define it like in 5C or 5A, this is an incomplete deglaciation. We also say that two isotopic minima are separate interglacials if the local maximum between them exceeds another threshold, this threshold here. If it doesn't, like between 7C and 7A, the local maximum does not exceed this threshold. Then the second one is a continued interglacial, so 7A is a continued interglacial. This is important because since there's no glaciation in between, there's no deglaciation, so the dynamics are quite different. The next thing we need to do is to define the insolation metric. And of course, the summer solstice insolation 65 degrees north has traditionally been used as a predictor for glacial changes because it represents maximum values at a sensitive time of the year, at a critical latitude. But we all know that 80% of the variance is in the precession band, and yet obliquity is important at high latitudes. We also know that the summers are shorter when perihelion is in June, which reduces the length of the ablation season. The Achilles heel, as Peter Huybers has called it. So we use instead the original metric used by Milankovitch, which is the caloric half-year summer insolation at 65 degrees. It's the energy integrated over the caloric summer half-year. And it turns out that around 65 degrees, this measure has almost equal contributions of precession and obliquity. And what we do next then, this may take some time to get used to it, but what we have is the caloric summer insolation in black over the last 2.6 million years, the Lysikian Ramo in brown, orange, over the same period. And what we've done is essentially we looked at every insolation peak, and we color-coded it whether in relation to the Lysikian Ramo curve. So if we have an interglacial defined here, then that peak is coded red. If it's an interstadial, like in stage 3, that peak is coded blue. And if it's a continued interglacial, that peak is coded black. The other thing we've shown here, the gray boxes are boxes during which obliquity is above average. It's above 23.3 degrees. And the thing to observe is that all the red dots occur in these gray boxes when obliquity is above average. Before 1 million years ago, every gray box is associated with a complete deglaciation, except one up here. After 1 million years, this is no longer the case. You start skipping some of the gray boxes. So that suggests that before the 41,000 year cycle, before 1 million years, arises at least partly because every second insolation peak is boosted by high obliquity. Okay? What I'll show you now, the next diagram takes these peaks, these color-coded peaks, and plots them against the last 2.6 million years. And what we see is that, well, it's impossible to draw some kind of horizontal line separating interglacials from interstadials, but before 1 million years, there is a threshold that we can draw here. It has one false negative, say 63, though there's some uncertainty over whether it's been assigned to the correct insolation peak. There's also another one, state 71, there may be a false negative, and the one around 2212. But those with open circles or open triangles represent uncertain assignments when you compare it to other benthic isotope curves. So there's some uncertainty over the assignment of those. But overall, it does a pretty good, simple job at separating the interglacials from interstadials. After 1 million years, we can draw a line here which suggests that the threshold has been raised, but it is impossible to define an interglacial space without including some interstadials as well. And if we look at those interstadials, 5A, 6C, 9E, if we look at them in detail, what we find is that they occur early in the glacial cycle, so they're not preceded by large ice accumulations. And that's a hint that maybe a simple rule needs to incorporate glacial history somehow. And we do this by saying that the propensity for a complete deglaciation increases with time elapses the previous interglacial onset. And this is an idea that's been around for a long time. It's the simplest way to incorporate the idea that over time, the glacial system accumulates instability that makes ice sheets more sensitive to insolation increases. It could be because of instability in the ice bedrock system, or a change in the ice albedo because of dust deposition or CO2 decasting over time. So what we do is that then we calculate elapsed time since the previous deglaciation for every insolation peak, and we plot this. So elapsed time on the y-axis relative to the caloric summer insolation for each peak. And you can draw a diagonal line separating the interglacials from the interstadials, very, very simply. And the y-intercept of this line over here, 6.14 gigajoules per square meter, is the deglaciation threshold for zero elapsed time. And what we see then, this line shows that the insolation threshold decreases linearly with time. And so therefore we can say that the slope of the line represents a discount rate for deglaciation. So we define the effective energy for deglaciation as the peak caloric summer insolation plus the time elapsed since interglacial onset plus the discount rate. And when this effective energy exceeds this threshold for deglaciation, we have a complete deglaciation. We plot the effective energy for each insolation peak for the last 2.6 million years. And what we have is, what emerges is an orderly arrangement now of complete deglaciations after 1 million years. And what we see over the course of the Quaternary is we have a simple insolation threshold here that seems to be getting higher, starting about 1.5 million years ago. And after 1 million years ago, you start skipping insolation peaks, which then leads to longer glacials, which then in turn leads to larger and more unstable ice sheets. We finally ask whether the sequence of interglacials of the last 1 million years is robustly determined. And we can see from here that some insolation peaks almost made it, but just a complete deglaciation was aborted. Others made it, others were aborted. And you can imagine that this threshold, there's some fuzziness around this threshold because of some changes in feedbacks or different forcings, volcanic, solar changes, or internal noise in the climate system. And so we then want to know to what extent changes, small changes, can alter the sequence of interglacials. And we do this by using a statistical model based on logistic regression to sample scenarios. About 25,000 Monte Carlo simulation turns out that the sequence that occurs more frequently is the one that has actually occurred. The next alternative is an absence of deglaciation at 7C. It then occurs at 6E. The next one is an absence of deglaciation at 11C, then occurs at 11A. And then deglaciation at stage 3 and no deglaciation at stage 1. And what is interesting is that we do not have a complete, if you alter the cycle at a particular sequence of interglacials, you don't have a change for, the whole sequence doesn't change. And it doesn't change because the extent of the modification is limited by some insolation peaks that are very strong, like 5e, for example, that are always going to be an interglacial. So therefore, we can now finally answer a question that Eric Wolf posed some time ago, whether starting from 2.6 million years ago, we found ourselves in an interglacial today. And the answer is, it depends on the history of stage 3. It's the extent of deglaciation in stage 3 that decides the fate of stage 1. And that raises some interesting counterfactuals regarding human history, but that's another talk. To conclude, we have developed an exquisitely simple, we think it's exquisitely simple, model to predict whether an insolation peak leads to interglacial onset based on a single insolation metric and elapsed time since the previous deglaciation. Before 1 million years ago, interglacials occurred when insolation exceeded a simple threshold every 41,000 years. Sometime around 1.5, there's a gradual rise in the deglaciation threshold, and I'm sure we'll hear more during the course of this session about this, which led to an increase in the frequency of skipped insolation peaks after 1 million years. So then what we're saying is that the larger ice sheets are a function of these skipped insolation cycles, which lead to longer glacials, okay, instead of the other way around. And finally, the succession of interglacials that has occurred in the last million years is the most probable and among a very small set of possibilities. Thank you.
That stage 3, stage 1 argument, how well does it work with 12 and 11 in terms of elapsed time and predictive strengths?
No, it doesn't.
Can you comment
on
that,
there's no direct comparison. No, it doesn't. You don't have the same situation. I mean, the stage 3 is a particular case. And all I'm going to say is that, maybe it turns out that Emiliani was right after all in calling stage 3, but, I'll talk to you about it afterwards.
So this is an amazing rule. Now, do you have any idea about the dynamics, why there are these changes suddenly at 1.5 and 0.5 million years?
No, I mean, there's various discussions. Of course, I think people in this room have talked about this over a long time. So I don't wish to, so there may be something with changes. We see changes in dust accumulation in the Southern Ocean, changes in a weakening of AMOC, and the northern component water, a bit more ice rafting. What is actually driving this? We don't, there's different hypotheses. So I'm not going to enter this. I mean, the idea is that we are observing something changing gradually. Something is raised in the deglaciation threshold. I wouldn't want to to get into further details.
Thank you to the organizers for both inviting and kind of allowing this talk, as well as putting one of my collaborators right behind me in the talk, which allows me to kind of essentially steal a double. Well, we can steal a double session and gives me maybe the easier job of saying, okay, well, this is going to be the answer to hopefully the answer to the orbital forcing and the CO2 forcing without actually having to explain too many of the mechanisms for why we see that change. Obviously, I have a whole host, an ever-growing number of co-authors associated with this project. It's probably too many to name. I can't even fit them all on this slide. But their help is greatly appreciated. So now we know that we don't really need CO2 to define the interglacials. I want to kind of show you hopefully what we think we can do. So it's great to be in this session, and I want, if you take away nothing else from this talk, I want you to take away these 3 points, which is that we have a delta 11 pH proxy, delta 11 boron pH proxy that represents, I think, a really important way to determine past changes from CO2. And I'm going to show you that this proxy is capable of reconstructing and resolving even relatively minor changes to the carbon cycle. And then from early in the NPT to the late Pleistocene, I'm going to show you that there was a CO2 lowering on average, which is going to be imparted mostly by a lowering of glacial CO2. So just to orientate you again, I was probably going to get sick of this slide during this session, but obviously we have the late Pleistocene glacials here, and we know the CO2 range from the ice core records, which are a fantastic archive. We know that CO2 was roughly between 180 and 300 parts per million. And then we know also in the Pliocene, which we'll probably hear about later in this afternoon session, where we think CO2 was above 400 ppm, right over there 3 million years ago. But there's this whole period in the middle where we see this deepening of glacial cycles, intensification of ice volume, and that's really kind of an unknown in terms of CO2 at the moment. The existing records are too low resolution to determine the CO2 cycles across this period. But we do have this major feature, which is the change from kind of 41,000 year pacing to a quasi 100,000 year cycle in the latest Pleistocene. And the null hypothesis might be that this is associated with a CO2 decline. So we have some sea level records across this interval, which could be interpreted as ice volume. So there's a plot from Ilko Rohling's paper in 2014. And it's kind of a stack of multiple different ways of reconstructing the sea level across the late and middle Pleistocene. So what we can see, the kind of features that most stick out to me are that we've got kind of interglacial sea level of around 0 through most of this interval. Like there's some variation, there's a little bit of noise in some of these proxy reconstructions, but we also have the late Pleistocene glacials where we have sea level of 100 meters or lower, suggesting a much larger buildup of ice on land. And these kind of peter out towards the mid-Pleistocene transition with some early kind of onsets at 900,000, but then you also seem to have some intervals in between where we see much lower ice volume buildup until you get really to the last 400,000 years. Equally, over here in this box, we've got quite muted sea level changes, and this is the interval that I'm going to be focusing on today. You can see that most of the sea level records in this interval agree with each other, and they agree that glacial CO2 sea level was a little bit higher. And then again, these kind of peter out towards the late Pleistocene glacials. So the kind of theories behind what might be controlling this really fall in at the moment to 2 kind of main camps. One would be a change of internal dynamics. So when you concentrate on this plot, we've got relative sea level on the y-axis and the radiative change resulting from CO2 forcing on the x-axis. So at the moment, our late Pleistocene interglacial glacial cycle comes from modern conditions or pre-industrial conditions down to a much lower sea level combined with a much lower radiative forcing. So that could be shown from basically going from kind of this kind of scenario here down to the bottom here. And the first kind of group of scenarios would suggest that we have a big change in ice dynamics, which would change the slope of this relationship. So we'd get a bigger change per unit of radiative forcing after this change in ice dynamics. A key kind of candidate for this might be something like the regolith hypothesis, where a loose sediment cover kind of erodes off from progressive ice sheets and allows thicker ice to build up on the continent, but associated with the same CO2 decline. So something that's really just internal to the ice sheet system. The other group of hypotheses would be that it's CO2 driven, and this is why we might need a CO2 record for this interval, whereby we would see the same relationship between sea level and radiative forcing, but actually just an absolute change in CO2 values, so going from high CO2 to kind of moderate value before the MPT, and then afterwards some additional drawdown of CO2 that allows this extra sea level and ice volume. Of course, we could also have a combination of both of these. So we're really fortunate in this time period that we're working in to have the fantastic ice core proxy. Let's call it the gold standard of paleo CO2 proxies, and this is the kind of ice core data for the last 800,000 years, and of course an additional little bit of work would show that we've come far above any value in this ice core record, so perhaps suggesting why we might need a really good proxy for going further back in time. One thing to note is that there is some ice that's older than this that's been reconstructed from the Allen Hills, and that's just shown in here. It's about 1 million years old, but it's not stratigraphically constrained. So these are the values of CO2 that they're getting out of the ice, but where it fits and maybe the order of those is a little bit unclear. And perhaps that's something we can help with by enhancing and getting a new CO2 proxy. So again, really fortunate to have this ice core record, because not only does it allow us to kind of have something to test our proxy on, we can also add an extra kind of calibration step into our data. So all the data I'm going to show you is from boron isotopes, which are a pH proxy and then can be converted to CO2. I won't go through that process today, but we do need a foraminiferal calibration. So we are using Hain et al. 2013 for the Plantic forum Globigerinoides ruber, which is a laboratory and core top and toe calibration. But the ice cores also allow us to do a validation or even a temporal calibration if we would like to. So we've got the ice core record here, as shown, and now I can show you some of our boron-derived CO2 from 3 different sites. So boron isotopes are a lot of work, so I can't claim all the credit for this. Elwyn de la Vega, a PhD student in Southampton, has provided a lot of the data from ODP 758 and 871, which are in the green and the yellow. Most of the data here is from ODP 999, which is all of the red data. And I think what I'd really like to kind of draw your eye to is the fact that we know we're getting multiple sites which are all in agreement over this period, and where we have kind of slightly lower resolution data in these lukewarm glacials, except for a few outliers, we are seeing pretty good agreement. So a really good extra thing we can do now, having this multi-site data, is actually combine them in some way which helps to cover the resolution and help us to beat down on the uncertainties. We're a proxy, indirect proxy measurement, and it's good to be able to lower our uncertainties. We'll never get as good as the ice cores, perhaps, but I think this is a really good start. So combining these 3 cores together, I think we have pretty convincing glacial interglacial cycles, but also the relatively minor CO2 changes on these millennial scales in here, particularly striking. We can actually resolve kind of 20 ppm differences in atmospheric CO2, and you can see that we're also recovering the lukewarm interglacials really well too. So there are still some problems, and we're still working on this. We have some flyers that are here that haven't been captured by my smoother, and there's also a slight mean overestimation of about 5 ppm on this record, but overall I think we're doing pretty well. So to move on to the early MPT boron isotope record, so back to that window where the sea level changes are a little bit muted, but crucially in good agreement. What we can see is we've got a now just all from the same site, which is ODP 999. So we're comparing like with like. We've got 2 equally well-resolved records, one from after the MPT and one from the very start of the MPT, where we've got this skipped obliquity cycle in here, which is kind of the first non-41,000 year thing. And what we see is that the boron isotopes fit very well with the oxygen isotopes. We're seeing reduced length cycles. So we've got 41,000 years and then an 80 kind of thousand year one in these early mid-Pleistocene transition interglacials. So when we convert that to CO2, and now we can also add the work by Berbel-Hernisch, which is from a different site, but kind of covering the same interval at a low resolution. And I think this gives us a little more confidence in our reconstruction from 999, where we can see that we have a kind of general global agreement. So things to take away here, we're seeing a much more symmetrical CO2 cycle from early in the transition, rather than these distinctive sawtooths in the late Pleistocene. We even see kind of a hint of the mixed obliquity cycle in here, where it kind of tries to start doing a glacial and then comes back out. But the main feature, I think, of it is going to be that whilst we see very, very similar interglacial CO2 values, the glacial CO2 is much reduced here. So just to put that in a kind of time series context, it's exactly the same data, showing that obviously we have a gap in here between where the kind of full NPT transition occurs. And to show that ice core data again, it's just going to be somewhere in this interval. We're showing we're in really good agreement with the data that's out there. So going back to our forcing scenarios, so we've got scenario 1, which was the change in some kind of internal dynamics, change in 2, which is additional CO2 drawdown, and then this hybrid scenario where we see actually both a change in gradient and a change in the absolute value of CO2 change, and we can now add data to this, and you can see that actually the hybrid scenario is what we're reconstructing. So we've got both a different response of sea level to CO2 forcing, as well as an overall increase in CO2. Important to note that it doesn't matter which sea level reconstruction we use for this. We can use any of them and we get the same reduction in gradient and increase in amplitude of these changes, or even just a simple cross plot of boron isotope versus oxygen isotope from the same site. So this is kind of the main conclusions, is that we see no observable interglacial change in any of our kind of 4 proxy estimates, and Mathis is going to introduce the Cyclops model in the next talk. But we have the results from ODP 999, 668, and the 1 million year old ice from Higgins et al. That show a stable interglacial CO2 change, a big decrease in glacial CO2 change over the MPT, and thus obviously a mandatory increase in the glacial to interglacial CO2 change. So hopefully I've shown that we've got a robust demonstration that we can use boron isotopes as a CO2 proxy, not just to resolve large changes in the climate system, but also these relatively small changes that are not too associated with enormous CO2 change. Also that we've got a distinct change in the delta radiative forcing, so change in radiative forcing for sea level relationship during the MPT and after the MPT. And that the MPT can neither be explained by changing just CO2, but nor can it be changed by just a change in ice dynamics or an internal feedback to the system. Thank you very much for listening.
I was just wondering, so you point out there's no change in the interglacial CO2 value. Did you try calculating the time average, by binning and calculating the average CO2 over the 2 periods, because there's a difference in the shape?
Yeah, so obviously there will be a difference based on, because obviously we have much shorter glacial cycles here. So I should have said the way we define those was by taking the oxygen isotopes, taking the top 25% and the bottom 25% of the kind of oxygen, so the interglacial and the glacial values, and then averaging the CO2 within that window. And actually, I think I might have that.
Sorry, did you also just average it over the whole
time? So it doesn't actually, it doesn't matter what definition of glacial or interglacial you choose. So of course, if you average it over the whole time, then you do get an average or mean CO2 decrease that is driven by the decrease in glacials.
Thank you, everyone, for attending, and thank you for the organizers for giving me the opportunity to talk about the simulation of glacial interglacial CO2 change across the mid-Pleistocene transition. And I will be rushing through the modeling part of this, so that I might get to that slide where I address the question why CO2 changed across the mid-Pleistocene transition. Just for context, I don't really want to talk about this figure. I do want to point out that the CO2 reconstructions before and during the mid-Pleistocene transition are too coarse resolution to actually address the question of the role of CO2 in driving the mid-Pleistocene transition, because obviously, the mid-Pleistocene transition is something that operates on orbital timescales, and these records don't currently resolve those. However, we have the I-square CO2 record for the late Pleistocene, and I've worked quite a bit on trying to understand what the mechanisms are that drive these changes that are obviously well observed in the I-square CO2 record. And without making a gross simplification here, we're going between glacials and interglacials. And during interglacials, we have deep water formation in the North Atlantic, NADW, and vigorous overturning in the Southern Ocean. Whereas during peak glacials, the Atlantic overturning is shoaled, and the polar and Arctic seems to have been more stratified with less vigorous formation and ventilation of the deep ocean. Also, there was much more dust being carried by the westerly wind belts onto the frontal system of the Southern Ocean, leading to iron fertilization. So that those are sort of the end members. But when we look at the I-square CO2 record, there's also many times when CO2 levels were somehow intermediate, and we would argue that there's some sort of mid-glacial climate carbon cycle state where the main difference to the current interglacial is that the polar and Arctic, the Southern Ocean, already seems to have been more stratified. Now, that's a very coarse view, and there's three elements that are changing. I just want to show very quickly how these mechanisms operate. So this is from sensitivity experiments with the Cyclops model, where I simulate net CO2 change driven by turning knobs that represent these different processes. And so the net CO2 change are the diagonals, and I parse those out into just carbon redistribution in the system. So you can think of that as the biological pump. That's the x-axis. And the y-axis is the open system calcium carbonate cycle response. So you can think of that as calcium carbonate compensation. And so the polar and Arctic mechanisms really, if I run a whole bunch of experiments to equilibrium, they really drive CO2 change mainly by redistributing carbon with a small amplification due to calcium carbonate compensation. So that's the polar and Arctic. If I shoal the Atlantic overturning, you can see that these arrows are either slightly pointing to the left or slightly pointing to the right. So that means that the response of the biological pump of the shoaling is dependent on the state of the Southern Ocean. However, mainly these arrows are pointing downward, which is to say that the shoaling of Atlantic overturning exposes a lot of calcium carbonate on the deep seafloor in the Atlantic, allows this calcium carbonate to be dissolved and the ocean to become more alkaline. So the dominant effect of the shoaling is actually to make the ocean more alkaline. The third one, that's the dust delivery onto the frontal system of the Southern Ocean, driving iron fertilization, more complete nutrient utilization. And so you see these arrows pointing sort of diagonal, which means that there's a large component of making the biological pump more efficient and a substantial amplification of that due to the open system calcium carbonate cycle. So that's the three levers, and so the notion is that coming from an interglacial state, the first step to this mid-glacial state is just driven by polar and Arctic changes. And then going to full glacial conditions is some combination of the initiation of iron fertilization and the shoaling of Atlantic overturning. And so to simulate, so if that is what happens in the late Pleistocene, we might be able to sort of extrapolate that back across the mid-Pleistocene transition just using proxy records that speak to these different processes. And I've chosen here a number of records that I will be using to turn the knobs in my model. Okay, so you might be familiar with sort of the standard forward modeling approach, where you take your model, you take some proxies, and you relate these proxies to the knobs in your model using some parameters. And then you just run the model and simulate CO2. So that's the forward modeling approach up top. What I've been doing here is, because Cyclops is really fast, it enables me to invert this approach. So I have the model, I have the proxies, and I do know the answer from the ice core CO2 record. And so I asked the question, what are the parameters that relate the proxy records to the knobs in my model? And so I'll be using these knobs as I described, and for this talk, I've also run an additional set of experiments where I have a background forcing based on the Elderfield deep ocean temperature reconstruction. So I incorporate the temperature effect. I incorporate also the inferred sea level changes. And so that will be shown in blue, and when I just turn these three knobs I discussed earlier, that will be shown in red. Okay, so here are the results of the inversion, and so the black is the ice core CO2 record, so that's the target of the optimization, and basically this slide should just show you that the optimization works. So it's not surprising that the model fits that, because that's what the optimization is designed to do. And there are some differences, but overall, both scenarios, both optimizations yield essentially the same result. So that's good. Now, Tom has boron isotope data, which is a pH proxy. And I have this is a full carbon cycle model, so I have all the carbon chemistry parameters and in it. And so I can directly compare his reconstructed pH to the pH changes that are in the model. And so this is for this early mid-Pleistocene transition time slice. And I guess all I want to say is that the match between the model and the data is satisfactory. I should point out that I have shifted the model by 6,000 years, which in my mind is the relative age uncertainty between the H model for the ODP 999 boron isotope data and the H models that underlie the proxy records that I use to drive the model. Okay, so the model is doing something very similar to what we reconstruct, and so this is really the result here. So if you look at the CO2 changes that I simulate, the highest interglacial CO2 levels are around 280 parts per million throughout the last 1.5 million years, which is as far back as I can go based on these proxy records. There are some glacial cycles, interglacials, that don't quite reach there, and the model seems to capture that where we have ice core CO2 data. There is a clear hint that across the mid-Pleistocene transition, glacial CO2 levels declined. Okay, so I think I made it here, and so here's the answer. It's a model, so I can knock out any one of the forcings that I include, and here in red and blue, those are the full model optimizations, and in black, that's when I knock out the iron fertilization forcing, so if I keep that constant. And I've arbitrarily drawn a line here at 220 parts per million. And if you squint, I hope you agree that mostly any CO2 that is below that line is there because of the iron fertilization forcing. So the black line hardly ever gets below that line, and only due to the iron fertilization forcing does CO2 decline below that level. Okay, so the answer is dust. Well, that's not surprising if you consider the dust record, and this is really the record that I used to drive that is Alfredo Martinez Garcia record, and just for fun, I've cross-plotted here the iron mass accumulation rate, so that's the proxy, and the simulated CO2 drawdown that I isolate, that is driven by exactly that forcing. And so then I can transfer that and basically calculate the CO2 effect directly from the full dust record. And essentially what I'm saying is that before the mid-Pleistocene transition, dust was maybe a 10 part per million contribution to the glacial interglacial cycles, but that contribution ramped up to become on the order of 30 parts per million after the mid-Pleistocene transition. And that's sort of, you have to look at every individual glacial cycle. There's some dusty glacials already sort of prior. Okay, so So to summarize that, I have included only the things that I believe are important for the late Pleistocene glacial-interglacial cycles. And it seems that those mechanisms are sufficient to capture the late Pleistocene. That's not surprising. But also they agree with Tom's boron isotope data. So I cannot rule out that there was any other additional process, but for now, given the data we have, it appears that we don't have to invoke any additional net change in the carbon inventory of the climate system. It's just a reorganization of carbon, a relocation of carbon, and the open system calcium carbonate response, driving CO2 change on glacial-interglacial cycles across the interval. The second point is that there is a change in dust, and that change is specific to glacial stages. So that is to say, if the dust ramped up, specifically during glacial stages, it exerts a radiative forcing during these orbital phases, and thereby helps stabilize the ice sheets. So that maybe the greater dustiness and associated CO2 drawdown are actually an important part in why ice sheets survive across multiple orbital cycles during and after the mid-Pleistocene transition. So it's Eric, it's not like there is a mean change in CO2 in the model, but it's not that there's a net change in the carbon inventory. And it's really the glacial specificity of the iron that drives that change. And then, yeah, so that's it.
You haven't shown the data again. So my remembering from the data was that it goes up to 300 ppm before the mid-Pleistocene transition. You said nothing about an increase in CO2 in the interglacials earlier in time. Can you comment on that? The data went up to 300 ppm, and you went up to 280.
Which data? So the point is that that individual boron isotope data points have a relatively large uncertainty. So basically, if I go here, basically you can see that for example here. If you look at the statistics, if you sample specific glacial stages or specific interglacial stages and estimate what the CO2 level was, the model and the data agree. Individual data points might be off. And if you look at the direct ice core CO2 comparison that Tom showed, there were specifically during interglacials, a couple of flyers that were just higher CO2, and we know CO2 wasn't 300 parts per million in the late Pleistocene. So it's really important to compare like with like. So if we compare the boron isotope, orbitally resolved boron isotope data from the late Pleistocene to the early mid-Pleistocene transition, we don't see a net change, and that's based on the statistics of the data itself.
I would like thanks the organizers, especially Eric, who sent me an email about this very interesting session, and also thank you, Chronis, you involved me in a future working group meeting about this topic. So today I'm going to talk about our recent work on high-resolution Jeanne record from the Chinese plateau. It's about the mid-Pleistocene monsoon transition from 23 to 100 key cycles. So this work was done by in cooperation with some modelers from Belgium and also paleoceanographer from the USA and some colleagues. And we know that 40 years ago, Shackleton and Uptake first generated a very detailed Pleistocene oxygen isotope record, this one, and they found they have a large amplitude shift around 0.9 million years ago. And then using time series analysis, the PCRs and more reveal that the frequency shift so just they mentioned they have a shift from 41 to 100 K cycles around 1.9 to 1.5 to 0.9 million years ago, and then in the past 3 decades they have a lot of record from the ocean, from the land, and also from lake sediments. They show this kind of mid-Pleistocene transition, and those proxies reflecting the changes in ice volume, sea level, temperature, or monsoon intensity, or source aridity. Here I just show you some representative record from global, and this is the AR04. This is a proxy of the ice volume or ocean temperature, and this is the temperature change, and this is the sea level, and this is the monsoon intensity, and this is the Indian monsoon intensity, and here is the record from Sasha, and this is another lake record from Northeastern Asia. So when you look at those records, most of those records show MPT from 41 to 100 K cycles. Here, some spectral result before the MPT and after MPT. You can say before the MPT, they have a very strong 41 K cycles, and after that, you will see a very strong 100 K cycles. But for this one, you cannot say very strong 100 K cycles here. So if you look at the monsoon record here, I just show this monsoon proxies exhibit very the intensity of 100 K cycle and 41. So this is some proxies from the Mediterranean Sea reflecting the Asian monsoon change. Here you can say glacial interglacial contrast, and also you can say precessional signal. And these two curves are from the Arabian Sea. They show was dominated by 23,000 year cycles. So when you look at the East Asian monsoon change, you have 2 different archives. One is the speleotherm, which show very dominant precessional cycles. But if you say the LSCE proxies, this is the carbon isotope, they show both 100 K cycle and the 23,000 year cycles. So why they have such kind of difference? So we just thinking that maybe due to the different sensitivity of proxy to temperature or to precipitation, or because of the different sensitivity of location to the insolation and ice forcing. Then why we study Chinese LSCE? Because LSCE is a kind of yielding dust transported by the winter monsoon from this region, so it's linked to high latitude climate change. But after the dust was deposited, the moisture transported from the low latitude tropical ocean by the summer monsoon can result in pathogenesis. So here you can see this kind of LSCE paleosoil sequence. The reddish layer is interglacial paleosoil, the yellowish layer is LSCE. So based on the yielding sediments in Chinese LSCE plateau, we can get the paleo monsoon variability from 25 million years ago to present. You can work on the tectonic to millennial scale monsoon variability based on this kind of yielding sediments. So here is a picture from the central LSCE plateau. You just pay attention to critical boundaries. One is here. Here is the Pliocene red clay. You see reddish layer here. And then here is the quaternary LSCE paleosoil sequence. And then here has another boundary, is 1.2 million years. This is we are interested in the MPT. And if you look one curve, this is the magnetic susceptibility change. This is a proxy of the summer monsoon intensity with higher susceptibility means a stronger summer monsoon, okay? So when you look at this early Pleistocene, this is a curve, this is the LSCE paleosoil alterations. You can see this sequence was dominated by 41 K cycles. And after that, you can see those kind of fluctuations show a dominant 100 K cycles. So if I start my talk here, you may imagine that, okay, Chinese LSCE looks more like a global climate change, but I don't want to stop here because most of previous works was on this region from the central plateau. Here, the accumulation rate is relatively low, and the pathogenesis is very strong. So if we focus on the last interglacial paleosoil, you will see in the southeastern Lurs Plateau, the S1 last interglacial paleosoil was only one soil complex. If you move to the northwestern Lurs Plateau, here, because of the accumulation is very high, you can see 3 sublayers here during the stage last interglacial. So that means you can see 5A, 5C, 5E here. So once you work on high resolution, there's sequence from the western Lurs Plateau. That means you can have a different understanding of the monsoon variability and dynamics. So we select one site from here. This section was accumulated on the terrace of the Yellow River. And here it's very hard to get fresh outcrops. So we got draining here. We have 430 meters Lurs core from this region and back to 1.7 million years. And then this is the magnetostratigraphy of our core. Because we didn't find our dewey here, so we suppose that the Lurs was accumulated here is younger than 1.8 million years. And then this is 3 proxies. This is green size. We can see it's a winter monsoon indicator. And this is a magnetic susceptibility, which was usually used as a summer monsoon intensity. But in the western Lurs Plateau, because the precipitation is relatively low, so during glaciers, you cannot see any kind of fluctuations. So we developed another sensitive proxy. This one is carbon isotope of Lurs carbonate to reflect the summer monsoon intensity. I will talk more about later. So the chronology for this long core was generated by correlating the green size with basic oxygen isotope for the last 1 million year. And before 1 million year, we just use linear interpolation of several time controllers from the geometric reversal or excursions. So then, why we think this one is very sensitive, and this is our curve, the carbon isotope of Lurs carbonate, and this is the Jeanne record, and the insolation and the green ice core. So our records show very clear interglacial and glacial contrast, and also precessional signal, and also this kind of Henrik-like events. So we believe that this one is the most sensitive indicator for the summer monsoon so far we found in this region. Then let's look at the long record spanning the 1.7 million years ago, this curve. And we just pay attention to the spectral result difference. So we do a spectral analysis for 4 intervals. So this is before the MPT. You can see this curve shows very dominant precessional signal, differing from the 41 of the basic oxygen isotope. And after 0.9 million years ago, we can say there have these two our Proxy and the basic oxygen isotope show similar 100 K cycle is very strong. So this is the spectral difference. If we look at the wavelength spectra of those two records, you can say, okay, for insolation, we have very dominant precessional signal and oblique signal. And then if you see S volume, okay, before the MPT, they have very strong 41 K cycle, and the 100 K cycle occurred around 1.1 million years, and it becomes stronger 0.9 million years ago. This is our result. You can say before 1.2 million years ago, they have very strong precessional signal, and then shift to 100 K cycle. This is a significant difference. Then if we look at the interglacial monsoon variability after MPT, if we define the interglacial using our Lurs proxies, the screen size and carbon isotope, we can get some general understanding that the duration of the last 8 interglacials ranging from 3 to 7 million years ago is different from the definition based on the basic oxygen isotope. And if we pay attention to this kind of fine scale oscillations, we will find some this is precessional, and during stage 11 and stage 19, this is kind of a half precession variability. So this is after MPT. When before MPT, if we look at this is our record. This is the India summer monsoon proxy from the Peral Lake. This is record from the Mediterranean Sea to reflect the African monsoon change. You can see before 1.2 million years, we have very strong precessional signal. So this is not in the Lurs Plateau. It's in other monsoon regions. So if we see the variability, okay, you will say we have very strong precessional signal here. But except for this one, the Indian summer monsoon, because our spectral result was done between 0.8 to 1.6. If we focus on this time period, okay, it's 23,000 years. So let's summarize. So we know that the MPT, is widely recognized as a shift from 41 to 100 cycles. But our high resolution, there's proxies show a different transition from 23 to 100 cycles across MPT. So this kind of MPT monsoon transition was likely caused by the competing effect of precision and coupled ice and CO2 forcing. So it seems that the insolation impact on monsoon variability after MPT was surprised when the northern hemisphere became more glaciated during glacial times. That's it. Thank you.
What a beautiful Del-C13 record. How does your carbonate Del-C13 agrees with Hain record of Del-C13 and speleothems? How do these things work together?
For the speleothem record, you mentioned the carbon isotope or oxygen. Carbon, I just heard some talk from the domestic meeting. They mentioned that the carbon isotope also show some interglacial fluctuations, but it's not published yet.
Try to match those.
Because they didn't publish it, so we cannot match.
Because you get a very high resolution for deep time. If there is a modulation in the Loess plateau due to the MPT, maybe you should see something when the Greenland ice sheets get glaciated. Do you see any changes? You can do that for 2.7. You get a good resolution. Can you see some changes at this time?
We have some. Let me show this one. So basically, this is the possible forcing of the monsoon variability, including the 3 astronomical parameters: eccentricity, precision, obliquity, and also ice volume or CO2. And we think that big difference before and after MPT is the glacier level of the ice and CO2. So this is a kind of hypothesis. We're allowed to do some modeling work to test what's the why before after MPT when they have a much lower CO2 and high ice volume will diminish the impact of the insolation in the future.
Thank you very much for the opportunity to speak today. I do have to acknowledge my postdoc supervisor, Mo Ramo, who I did a lot of this work with, as well as the entire Lamont community. You'll hear a talk later from Leo Pena looking at some of the other neodymium and boron calcium records that we've been generating over the mid-Pleistocene transition. Okay, so if we look at it's a sort of a false controversy, but there are kind of 2 different interpretations of the mid-Pleistocene transition. One is that it's gradual or that it was an abrupt transition. And this is time on the horizontal axis. On the vertical axis, you have the benthic oxygen isotope. And the simple interpretation of the benthic oxygen isotope record is that you had a gradual increase in ice volume and or decrease in temperature. But what I wanted to point out is that there's 2 really significant events in this record. At MIS 22, you see the statistically significant emergence of the 100,000-year cycle in many of the benthic oxygen isotope records. And at MIS 16, you have this large increase in the benthic oxygen isotope record, and the mid-Pleistocene transition is more or less complete. The main ideas as to why this transition is happening is that you had gradual global cooling, which may or may not be related to CO2. There were changes in ice volume and or ice sheet dynamics. And there's also possible changes in thermohaline circulation reorganization. And this isn't a comprehensive list of ideas for the mid-Pleistocene transition in terms of the mechanism, but these are the ones that I'm going to be talking about here. So part of the difficulty of interpreting the benthic record is that if you look at the benthic oxygen value of calcite, it reflects both temperature and the delta 18O of seawater. And we can use magnesium calcium values of benthic foraminifera to constrain this temperature component, This is just a simple calibration by Harry Elderfield with temperature on the horizontal axis and the magnesium calcium on the vertical axis. And you can see that magnesium substitutes in for calcium, and that's a temperature dependent substitution. So you can look at temperature, and there's some component of global. Are you in a glacial? Are you in interglacial? And there's also the local component. So where is that water mass come from, and what were the conditions at the formation regions, specifically for bottom waters? And then the other part is the delta 18O seawater, which is simply interpreted as an ice volume signal. But I want to point out this is also has a salinity component. So what were the characteristics of those formation regions and the evaporation and precipitation? So unfortunately, there's only very few magnesium-calcium records, high-resolution magnesium-calcium records that exist right now to try and parse out this temperature versus ice volume component. One is from the North Atlantic 607 here, originally done by Sozdian and Rosenthal in 2009. And there's a really lovely high-resolution record from the South Pacific at 1123. And most of the talk I'm going to be focusing on this new record that we've generated from the North Pacific, site 1208 on Shatsky Rise. And this site is a good indicator of possibly conditions that are going on. Today it's in the North Pacific deep water, which is the most voluminous water mass and also the most well mixed. So if we look at the previously published records, the 607 record suggests that there was a gradual bottom water temperature decrease over the mid-Pleistocene transition, whereas we look at the South Pacific record, it suggests that there was an abrupt increase in ice volume. So just to look at the North Atlantic again, this is the benthic oxygen isotope record here. And if we parse out the magnesium-calcium to the temperature, you can see that there's this bottom water temperature cooling trend that Cindy showed and the temperatures. And when you back calculate out the delta 18O seawater, that delta 18O seawater is relatively stable over the mid-Pleistocene transition. However, this record had been questioned because the two species that Cyndia used, Wollerstrophi and Umbanatus, are known to have changes, or their magnesium-calcium values are known to be affected by changes in carbonate ion saturation. So one thing that we did is we revisited site 607, and we looked at, we did the magnesium-calcium values of Youbin, which are here in blue, which are not thought to be influenced by carbonate ion concentration. And what you can see is that each of the species, the Umbanatus, the Wollerstrophi, and Youbin, if you look at the broad general trend, they all support that there was a gradual decrease in bottom water temperature over the mid-Pleistocene transition. That's not to say that the carbonate ion doesn't affect the Wollerstrophi magnesium-calcium values, but the general trend is that there was a gradual bottom water temperature cooling over the mid-Pleistocene transition if we look at the North Atlantic. And that suggests that there was little change in the delta 18O of seawater. So again, this is the LOR4 stack. You have time on the horizontal axis. And this is the new benthic oxygen isotope record that we have from the North Pacific. And what you can see is that the structure and the timing events is actually really comparable to LOR4. You have a gradual decrease here in the benthic oxygen isotope values, and there's this large step here at MIS 16. Again, this is the North Pacific record that we just generated. If you compare that to the South Pacific record, they're actually different, and this is interesting because they're both in the same basins, but the South Pacific record is relatively stable in the early Pleistocene, and its large step happens at MIS 22. What does this mean in terms of if we now subtract out the temperature components? This is the benthic oxygen isotope records, again, from the North Pacific. This is our bottom water temperature record based on Youbin. Unfortunately, we don't have a lot of samples here, but in general, what we see is that the glacial values are relatively cool. There's not a gradual bottom water temperature change if you look at the North Pacific. But interestingly, at MIS 22 and possibly at MIS 16, we see a warm temperature trend during these time periods that are supposed to be pretty strong glacials. And then if you look at the South Pacific record, this is Harry's record, you see a similar story in that there's no bottom water temperature trend and the glacials have near freezing temperatures for the length of the record. So the Pacific Basin itself has similar temperature trends, but if you look at the North Atlantic, you have this bottom water temperature trend. But these are different water basins. The fact that they have different temperature trends isn't the end of the world. What does matter is what do the Delta 18O seawater reconstructions say, and what does that tell us, or what does it help tell us about ice volume changes? So again, looking at the North Pacific record and then calculating out what the Delta 18O seawater has done, we have these large Delta 18O seawater excursions almost at MIS 22 and at MIS 16. So I think the important thing to see here is that you have relatively constant values here in the early Pleistocene. There's this large excursion here, but then at the next glacial at MIS 20, you have similar values as to your early Pleistocene. There is this one little blip here, and that's related to this warm bottom water temperature flyer that we have that there's not enough Euphydrina to replicate. And then you have this excursion again at MIS 16, and then it goes back up and is absent in MIS 12, which is the next strong glacial. So this is a bit unusual. If ice volume was growing, you would expect that the Delta 18O seawater would persist during these time periods. If you compare this with the South Pacific record, it looks a lot different, actually. So this is the Delta 18O seawater is relatively constant in the early Pleistocene, and then the South Pacific, it increases at MIS 22 and stays relatively stable for the rest of the late Pleistocene. So if these Delta 18O seawater reconstructions are meant to be ice volume, you would expect them to all record the same signal, right? Because ice volume is a global signal. So it's a little curious that they're not. So it's possible that in addition to any ice volume signal, that there might be changes in salinity that are happening as well, and changes in ocean circulation. If we were to strictly interpret these excursions as salinity, so no ice volume contribution, this would suggest that there was a salinity excursion of about 0.6 and 1 during MIS 22 and MIS 16. And this seems quite large, but when you compare that with some of the salinity excursions that we see, if you compare the most recent glacial to the interglacial, you do see about a 1 per mole shift in salinity. And if you look at the South Pacific record, it's about a 0.3 shift. And again, the North Atlantic record doesn't really show that much. So why might we be seeing the differences in these records? If this is ice volume, we should be seeing the same story. But part of this is related to the fact that there was thermohaline reorganization during the mid-Pleistocene transition, and it's also possible that the characteristics of where deep water masses are forming changed as well. So did the salinity balance change in the North Atlantic, and did it also change in Antarctica? And I think for thinking about the existing records that we have, this is just the carbon isotope records for the modern ocean and the glacial ocean. We can see that 607 is located in this area where we do see changes in the importance of the water masses. So that Delta 18O seawater reconstruction is probably affected by that. And if we look at the South Pacific record as well, you're also seeing that its location is relatively sensitive to the importance of different water masses. So if this changes over glacial and interglacial timescales, and also over the MPT, this is going to influence our Delta 18O seawater interpretations. So one of the things that we're suggesting is revisiting a hypothesis that was suggested by Mo in 2006, is that for the mid-Pleistocene transition at MIS 22, you saw the transition from terrestrial-based margins to marine-based margins. So Leo's going to talk about it later. If you look at the neodymium and the carbon isotope evidence from the pre-MPT interval, so if you look at the dominant water masses, the northern component water and the southern component water on glacial and interglacial timescales, there's not much variability, but the northern component water is pretty, it basically floods the Atlantic basin. When you get into MIS 22 or around this time, this is the time that we suggest that the ice sheet transition to a marine-based margin. And during this time, from the neodymium records, we see that the southern component water basically floods the Atlantic. And we think that this is due to the fact that when you transition to the marine-based ice sheets, and also during this time you had a relatively low southern hemisphere insulation, you had extensive ice sheets. Basically, you were flooding the Atlantic with this very salty, highly stratified water. And then after the MIS-22, you transition to interglacial times where you have strong northern component water and weak southern component water. And then the post-glacials in MIS-22, you had this strong, salty southern component water and a relatively weak northern component water. So essentially what we're suggesting is that since you're seeing these changes in the water masses, this is when the salinity stratification becomes important. So a lot of the really great talks happening earlier this week talked about the Southern Ocean's contribution to stratification and how that salty water might be contributing. So we suggest that MIS-22 is when this salt stratification mechanism really became important. MIS-16, we don't necessarily have a good process or but we think that it has to do with the fact that the Nordic heat pump was changing during this time. So I'm running over a little bit, but just to quickly recap, we see large delta 18O seawater excursions in the North Pacific. The MIS-22 transition that we see was related to terrestrial to marine-based Antarctica. This is when we also think that salinity stratification became important. But really, this last point came from discussions with David Hodell, who's going to be talking next and showing also a really nice high-resolution record. We really need multiple delta 18O seawater records to really evaluate the ice volume growth because we're seeing the changes in ocean circulation impacting these interpretations. So.
Really cool data set, Heather. Thank you very much for a nice talk. I was wondering, some of the hypotheses about changes in water mass or ventilation might be testable with the carbon-13 data, even though it is Euvigirina. Have you had a look?
Well, we talked about this a little bit. You mean the North Pacific record? Or, the North Pacific record looks a lot like the 849 record. So there's not, and in terms of, I don't know. The answer is I don't know, but it basically looks like mean ocean carbon. But I wouldn't expect the stratification signal to necessarily be very important in the North Pacific. It's more of the stratification in the Southern Ocean and how that water mass is proliferating out.
Well, we know that across the mid-Pleistocene transition that the climate system shifted from a dominantly 41 kiloyear obliquity cycle to a quasi-periodic 100 kiloyear cycle. The question that I'd like to address this morning is, how did millennial scale climate variability change across the MPT? And to do this, I'm going to show a new record from the so-called Shackleton site, site U1385 here on the southwest Iberian margin. I don't have a lot of time to tell you about the background in this in terms of the stratigraphy and the composite depth and age model. I just referred you to this paper, which was published in a special volume of Global Planetary Change. Now, the rationale for drilling Site 1385, the Shackleton site, was based on Nick Shackleton's kind of classic work on piston cores from this margin. And what Nick showed is that the planktic oxygen isotopic record of G. boloides, shown in red on the Iberian margin, resembles in great detail the Greenland Delta 18 record, such that, particularly in stage 3, essentially all the DO cycles are recorded. And moreover, he noted that the benthic 018 record from the Iberian margin, shown in gray, again resembles the Delta D record from the Epicodome sea ice core. So essentially in one marine sediment core, you have representation of both polar ice cores in Greenland and Antarctica. So what we've done is basically to extend this record to the base of 1385, which is about 1.45 million years into marine isotopic stage 47. So on the top is the planktic oxygen isotopic record on G. beloides, and on the bottom is the benthic O18 record on Cibicidoides williffsdorfi. So just some general characteristics of this record. If we look at the Holocene planktic O18 value, we see that throughout most of the interglacials, the last 1.5 million years, the planktic O18 value is essentially the same as the Holocene. There's a very nice poster by Teresa Rodriguez who did alkanone SST, and it shows the same response. So we don't see, for example, the lukewarm interglacials. However, in the benthic O18, you see that the interglacials, beyond 400,000 years, clearly have higher delta O18 values than the last 400,000 years. Now, turning our attention to the maximum benthic O18 values, the highest values are recorded actually in marine isotope stage 16 and 12, when the delta O18 actually exceeds 4.5 per mil. Stage 6 and stage 2 were also relatively high. There's kind of intermediate delta O18 values during all of these glacial stages, all the way back to stage 24, and then a few high delta O18 values also in this period in 32, 34, 36. And this yellow line represents kind of intermediate delta O18 that is similar, for example, to marine isotope stage 3. And we see here in the 41K whirl, older than 1.25 million years, that the glacial benthic O18 values were similar to marine isotopic stage 3. So as Heather showed in the last talk, that benthic O18 is not ice volume, yet it has to be corrected for temperature. We can do that using magnesium calcium. And we've done that at low resolution. The magnesium calcium temperature of Youbin is shown here in the orange record, and the blue record is just the benthic O18. And what I've done is I've scaled it so that 1 degree C in bottom water temperature is equivalent to about 0.25 per mil in delta O18. So if the amplitude of the orange and blue curves are the same, then you can explain all of the benthic O18 via temperature. And what I've done here is just to highlight the difference, which means that you have to have ice volume. And what you see is that in the 41K whirl, all the values are pretty much the same. And here at about 1.25, there's kind of an increase in stages 38, 36, 34. And then it sort of goes back, and then also you have relatively high del W values during stages 22, 20, and 18. The real monsters are these two, stage 16 and stage 12, and again, kind of lower del W values for stages 2 through 10. If we compare that to the Elderfield record, del W record from 1123, as Heather noted, there are some similarities and some differences. The main difference, of course, is that in Harry's record, the main drop occurs at 900,000. And the exception here are these three glacial stages. So if you were to kind of remove those, you would see more of a step-like change similar to the 1123 record. Okay, so what I really want to focus on, though, is the planktic O18 record. And again, what Nick showed is that during the past 120,000 years, that planktic O18 resembles in great detail the Greenland ice core record. So the question is this 1.45 million year record a proxy for the Greenland ice core record? And it would assume, right, that this coupling between, at least on millennial scale, sea surface temperature changes on the Iberian margin and Greenland temperature held. Okay, so one of the things I want to do is to kind of remove the orbital signal to focus on the millennial. And the way I've chosen to do that, there are a number of ways one could do that. One could use a high-pass filter or so. But what I've done is I've taken basically a Gaussian interpolation window of about 15 kiloyears, and that's shown in blue, and then calculated basically a residual to emphasize the millennial scale changes. And, okay, yeah, so this shows it what it basically looks like for the last 24,000 years or so. And again, you can see that the residual shows basically all of the DO variations during stage 3. So now we can do that for the full 1.5 million year record. Again, the GINT record is in blue. And then the residual is the difference, basically, between the red record and the blue record. And, okay, it looks like noise, but actually if you focus in, it's not. You see all of this very detailed millennial scale variability. And one thing that comes out from this is that there was persistent millennial scale variability throughout the last 1.5 million years. And I've tried to identify times that had, say, exceptionally high millennial variability just by identifying, by these red dots, points that are greater than 2 standard deviations, right, away from the mean. And I'll use this kind of as a calibration for other records. Okay, so now again, this is the Planktic and Benthic 018 record, and those basically are the 2 standard deviations, which tells you where there's very strong millennial variability. And I'd first like to focus on where you don't see strong millennial variability, which is basically the gaps, right, in this red signal. And it turns out, and this is no surprise, like the Holocene, all of the full interglacial periods, right, have very suppressed millennial scale variability. And in addition, the really large glacial intervals also have suppressed millennial variability. So you can see here, for example, stage 16. So most of the millennial variability is associated with a climate state of intermediate ice volume. Okay, so now this is the Planktic 018 record now in 500 kiloyear increments, so 0 to 0.5 million years on the top, 500 to 1,000 kiloyears, and then 1,000 to 1,500 kiloyears. And this is a really rich record. There's a lot of things I could talk about, but I just want to emphasize kind of a few details. So first off, if we look at the base of the record in the 41,000 year world, we see that, again, the glacial periods in the 41,000 year world had very strong millennial scale variability. Again, that's the 2 standard deviation about the residual. And then this is just the obliquity record overlain. And again, you can see during obliquity minima, during each of the glacials of the 41K world, we have high millennial scale variability. You can see that things begin to change here at about stage 38, 37, in that this is really the beginning of the mid-Pleistocene transition. And as we begin to go through the mid-Pleistocene transition, the signal changes a bit in that we have high millennial variability associated with obliquity minimum, but they tend to occur now on the transitions, on glacial inceptions from the interglacial. There's a good example here from 35 to 34. Very high millennial variability at this glacial inception. And this sort of continues into this interval from 1 million to 500,000. Again, if you look at the obliquity minimum, they tend to be associated with increased millennial variability, again associated with glacial inceptions, transitions from glacial to interglacial periods. And then if you look at the last 500,000 years, this relationship between obliquity and millennial variability it falls apart essentially in the 100 kiloyear whirl. So again, we see the most millennial scale variability when we have an intermediate benthic 018, so presumably intermediate ice volume. And I've defined this, as you can see here, as the so-called millennial window where you find increased millennial variability. So what happened across the mid-Pleistocene transition is kind of shown by this cartoon. So this area, this kind of orange area, represents the intermediate ice volume state, the millennial window, that in the 41K world, what you see is that the glacials were entirely within the millennial window. But then as we transition across the MPT, the climate system, if you will, goes through the millennial window on glacial inceptions and also briefly on glacial terminations. And also when you have long intermediate ice volumes like stage 3, which is somewhat exceptional for the 100K world, but looks quite similar to the 41 K whirl. This shows the relationship between Planctic 018 and benthic C13, and these are very tightly coupled. There is a change in benthic C13 here at 900,000, and Leo Pena is going to talk about this change in deep water circulation. And what I want to show you is that this extends to the millennial scale. So I'll just show you kind of three windows. And the Planctic 018, again, is at the top. The benthic C13 is on the bottom for these three windows of time. This is the last glacial period. And what you can see is that, again, each of the cold periods, the increases in Planctic 018, are associated with minima in benthic C13, suggesting that these temperature changes are not just a local phenomena, but they're coupled to changes in the overturning circulation in the North Atlantic. You can also look at this in kind of frequency domain. If you do a power spectra of the residual, what you see is that most of the higher frequency is in this range of maybe about 11 kiloyears to 3 kiloyears or so. Some of these frequencies are kind of familiar. For example, Heinrich events about 7 kiloyears. Some of them, like 11.5 and 5.5, even look like they might be harmonics of precession. And again, you can see on the wavelet that the millennial variability extends the entire way. Okay, so I'm just going to kind of summarize with kind of some heuristic diagrams. So this is modified from Jerry McManus's work. And Jerry, in his paper in '99, was the first to say that basically it's the intermediate ice volume states that are associated with the greatest millennial variability, the so-called sweet spot of Eric Galbraith's talk on Thursday. So full interglacials tend to be quite stable, or in Eric's terminology, too warm, and full glacial conditions also tend to be stable, too icy. So what happened across the MPT, and I'll just use Didier Payard's kind of tri-stable state cartoon to illustrate that, is in the 41K whirl, we're basically cycling from interglacial to kind of intermediate glacial state with high millennial variability throughout the glacial period. And then what happened across the MPT is that we, at least through the MPT, kind of moved into the full glacial, and then after 100,000 years, we seem to always go through this cycle where we have reduced millennial variability during the full glacial, and then we go through it briefly again on the termination. So I think I'll just end there and leave my conclusions up for you to read.
That record gives me kind of chills. It's so beautiful. That's not all I wanted to say, but it is just amazing. It's so cool. How often do you see stadial type events within a full interglacial? Because that's kind of an important question for where we may be headed.
Again, it depends on how you define an interglacial, but if you kind of define it via the pigs or quigs way, you actually see almost no millennial variability. It's very damped during the full interglacial. You do see it, like, for example, like in stage 5, there is millennial variability, for example, associated with 5B and 5C. That tends to sort of be related to precession, or like in stage 21, where you do see millennial variability, it seems to be like the 5 kiloyear semi-precessional cycle. But in general, the interglacials are kind of quiet, and the intermediate glacials are noisy. Full glacials are quiet again.
Hello, everyone. I would like to thank the organizing committee for allowing me to be here today. And before I start my presentation, I would really like to thank all these co-authors. You may notice the long list of co-authors, because this is truly the heroic effort of many different people over the last few years. And in particular, I would like to highlight a few names. There are like 3 people from this author list which are in this meeting. Heather Ford, which just gave us a beautiful talk before, but also 3 grad students, Mayan Yehudai, Yuhi Kim, which unfortunately couldn't be here, but Maria Jalmasegi is also here, and as well as Laura Hayes And the three of them presented 3 beautiful posters this morning. If they are still up, I'm not sure. I encourage you really to go and have a look at them. So I'm just the front face here for this talk, but just a little bit of history. Heather gave us a beautiful introduction on what are the main current ideas to discuss the NPT. So a few years ago at Le Monde, a bunch of people started discussing about this, and we said, okay, how about we apply some of the new deep ocean circulation proxies that we have to this and see if we can actually improve the knowledge for these deep ocean circulation changes across the NPT, or just come up with some new findings about it. So what we did is we decided to go to 2 well-known sites in the South Atlantic with reliable stratigraphy across the NPTs, ODP sites 1088 and 1090, okay? And we decided to apply the neodymium isotope proxy in these 2 sites. You may notice here that site 1088 is at the upper edge of the NADW, whereas site 1090 down here, it's at the lower edge of NADW. So if we see actual changes in the deep ocean circulation during this time, therefore neodymium isotope should be able to tell us whether this water mass was moving up, down, retreating, or actually becoming stronger. So we did that. Let me walk you through this plot, which might be familiar to some of you. We have H here in the x-axis. The blue line and the pink line correspond to the benthic isotope stratigraphy that Dave Hodell published a few years ago. And the dots that you see here correspond to the epsilon neodymium measurements that we did at glacial and interglacial peaks. So the red dots correspond with interglacial peaks for each one of these cores, whereas blue dots correspond to the glacial peaks at both sides. So I'm not going to go into the neodymium systematics in here because we don't have much time about it, but in very simple terms, what you can expect is that more negative values for epsilon neodymium correspond with stronger AMOC, the stronger presence of North Atlantic source waters into the South Atlantic, and the other way around. More positive values of epsilon neodymium would correspond with a weaker AMOC, therefore less Northern Atlantic source waters at these 2 sites. So the first thing I want you to notice about this is that if we look at the post-NPT described here at this transition time around 900 kiloyears, is that there is a significant difference between interglacial epsilon neodymium values and glacial epsilon neodymium values. This is pretty much the standard knowledge that we have for the LGM, for instance. This is a standard conceptual model where during glacial times we will have a slower deep ocean circulation with slower AMOC all across the basin, whereas during the interglacials, this a much more active convection into the deep ocean. Therefore, we would expect to see more North Atlantic source waters into the South Atlantic. All right? But the striking thing is that when we go to the pre-NPT period, we see that this difference between the interglacials and the glacial periods at both sides decreases significantly. This is about 2 epsilon units difference in the post-NPT period, and it's less than an epsilon unit for the pre-NPT period. And as I will show in my next slide, that's a huge change for the deep ocean. Another interesting thing happened, what we would like to call the NPT AMOC crisis around 900 kiloyears ago. In that case, we see a huge drop, a very large drop of epsilon neodymium values during this glacial time, MIS 24, but especially the interglacial MIS 23, we see even higher values of epsilon neodymium. That means that this could be interpreted in terms of neodymium as an unprecedented AMOC crash during this interglacial. Okay? And one of the beauties of working with neodymium isotopes is that using very simple binary mixing models and making a few assumptions, we can actually use this proxy to estimate the percentage change in the contribution of the relative end members. In this case, North Atlantic source waters versus southern source waters. If we do that, and you can see the scale here, the percentage of North Atlantic source waters through time, we can actually show that, in particular, during this time period here, MIS 23, when we compare with epsilon neodymium values that have been registered in the South Atlantic during the Heinrich Stadial 1, we have the same intensity. So from the neodymium point of view, we can tell that MIS 23 in the South Atlantic was equivalent to the Heinrich Stadial 1. That's a huge finding in terms of the proportions of waters that get into the South Atlantic, right? Another interesting discovery that we made was that this period here also coincided with with a drop in the atmospheric PCO2. We just saw before beautiful talks about the PCO2 reconstructions. I'm looking forward to play with this data, but comparing with variables data a while back, there seems to be a fairly good agreement that shows that when the ocean really slowed down, there was also a significant drop in the atmospheric PCO2. And finally, just as a curiosity, if you just sum up the age difference between MIS 25 here to MIS 21, all these intervals here essentially account for like 100 kiloyears interval. The deep ocean for 100 kiloyears essentially had a very, very slow circulation. The AMOC was really weak during this interval. All right, so that allows us to elaborate a very simplistic conceptual model for the pre-MPT, post-MPT intervals. But I want to get now to the point. Where are we now? Okay, have we come a long way ever since we published that? And the answer is yes. We have been working heavily on many different sites across the Atlantic. The idea is to create meridional oceanographic sections of epsilon neodymium, as well as other proxies like boron calcium, as Laura Hayes showed in her poster this morning. All right, so in theory, we will be able to create meridional epsilon neodymium profiles through time that would allow us to understand the internal structure in terms of circulation for the entire basin. So, just as I said, Laura and other people at Le Monde are working heavily in different proxies, and we are coordinating the efforts. We are working exactly the same samples, measuring neodymium isotopes, and then trace elements, boron calcium ratios. Just as a brief highlight, and I really encourage you to talk to her, she's also showing very consistent results on the carbonate ion content of the deep ocean that would really go or make sense with the neodymium data that we present. Okay, just earlier this week, Injo Wu presented a beautiful epsilon neodymium section in the South Atlantic. This is modern epsilon neodymium seawater data, together with Lambelet et al. That was published last year. So what you see in the lower plot is a meridional section of epsilon neodymium of the modern ocean. And these are all the sites that we are currently working on, and a few more on the way. I'm going to just present data from 607, 926, 1267, 1090, and 1088, okay, because these are the ones that we have more data so far. And what we would expect from the neodymium point of view, essentially, just looking at this section, at the modern section, we see a north to south gradient in epsilon neodymium values. We have more negative epsilon neodymium values in the North Atlantic, all right, and less negative epsilon neodymium values in the South Atlantic. So here's the data. Let me walk you through this plot. In the upper section, we have the LRO4. The solid dots correspond to interglacial peaks. The open dots correspond to glacial peaks. We have followed the same the same sequence in the epsilon neodymium values, and we have color-coded north to south the different sites that we are working at. So you see in purple and blue the North Atlantic sites, and in green, yellow, and red the South Atlantic sites. So the first thing that strikes your eye is that it actually, as you go south, you have more positive epsilon neodymium values, which is consistent with what you would expect from the neodymium point of view. So northern sites overall show more negative values, whereas the southern sites show more positive values, okay? But when you look into the details, if we zoom into the MPT, we can see really striking features. For instance, we can see that all these sites show the same pattern through the MPT interval. All of these sites are actually indicating a slowdown in the AMOC circulation through that interval. We go from very negative values here in the North Atlantic to more positive values down here, and the same happens at the equatorial sides and at the South Atlantic sides. Okay? So there seems to be a pretty consistent pattern here. At the same time, all the MPT sites show an unprecedented shift to a more southern-like signal. These more positive values might indicate in the South Atlantic that we didn't have enough North Atlantic source water getting to that site. But now we can say that even in the northern sites, we see the arrival of southern source waters to very high northern latitudes, which is something that we didn't knew before, okay? So now we are getting a much global picture of the entire basin. So one of the theories that we would like to throw out is that the data are consistent with a northward incursion of southern source waters into the entire basin across this interval. Now I want to focus on this particular site, 607 in the North Atlantic. And this is just a beautiful record that Yuhi team produced at Le Monde. this is the same plotting sequence that I showed before. So red corresponds with interglacial peaks, whereas blue corresponds with glacial peaks. And we can see now that we have extended this curve to pretty much to the, for the last 1.5 million years, that the same pattern that we show for the South Atlantic is also true for the North Atlantic. The glacial-interglacial difference in terms of epsilon neodymium for the pre-MPT period is fairly small, fairly reduced, but after the transition, we see that the amplitude of this has increased significantly. Another interesting feature is that interglacial values pretty much agree really well with the present-day North Atlantic deep water and member, and they haven't changed much through time, except for these few interglacial periods right after the what we call the crisis. Okay. On the other hand, the glacial values they have gone from very negative values, meaning very active AMOC. They've gone through this shift here across the MPT, and then they remain more positive, indicating a reduction in the AMOC circulation. Okay? So if we think about this in terms of carbon-13 and epsilon neodymium space, now we are going to introduce the stable isotopes in the picture. We can see really interesting features, like the interglacial epsilon neodymium and carbon-13 are relatively stable during the interglacial maxima, as you can see from these purple dots here and this yellow shading here. So I didn't say that, but the solid dots correspond with interglacial maxima and the open dots with the glacial maxima. Also, the color coding indicates that the yellow areas are pre-AMOC crisis values, and the purple data corresponds with the post-MPT interval. But as you can see, there are a few, on the overall consistent pattern, there are a few marine isotopic stages that stand out, namely MIS-26 and MIS-23. So we would like to propose is that in this case, MIS-26, which you can see here as a very negative glacial just before the crisis, might have been triggered by the contribution of terrestrial material from the Northern Hemisphere shield across the Canadian and the North America craton. So we think at this point that during this interval, there is some strong Northern Hemisphere preconditioning event, if you say, in the upper North Atlantic that might have somehow triggered these large excursion in epsilon neodymium. And I'm just running out of time, just want to say that when we do the same comparison for the entire basin, the pattern holds. The carbon-13 and the epsilon neodymium agree really well on a basin-wide scale. We do have the interglacial mixing line here and the glacial mixing line here. And when you compare the north to south sides, they fall pretty well, or they seem to agree pretty well with this mixing line. So just to sum up, I want to say that north to south epsilon neodymium values are consistent with the stronger North Atlantic source waters, and this is strong evidence that the data do indeed reflect the AMOC changes through time. The MPT AMOC crisis is seen all across the entire Atlantic, and it confirms that a basin-wide impact and also consistent with the arrival of southern source waters after the MPT into the North Atlantic. Finally, just an idea that we would like to throw out is that the epsilon neodymium excursion just before the MPT indicates a spike of northern hemispheric shield material into the North Atlantic, and that might be a potential evidence for a northern hemisphere trigger for this. Thank you.
I'm not sure the neodymium C13 will answer this, but yesterday Jasmine Link showed from the Bermuda Rise that you can get very different source waters of North Atlantic deep water with very different epsilon neodymium through different interglacials or different parts of a single interglacial. And if I remember correctly, you could explain the MPT with just a massive flood of Nordic seawater coming down the Atlantic. Does the C13 allow you to rule that out, or is that still a possibility that rather than shutting off AMOC, you actually are flooding the Atlantic with Nordic seawater which has the right epsilon neodymium? Hi,
Bob. To answer that question, I would really encourage you to talk to Maria Jaume-Seguí. She has a lot of data of 1063 all over the MPT. I didn't show this data here, but there seems to be a particular feature about that side, and that's that during interglacials, the epsilon neodymium values are extremely negative, and they are not consistent with any water mass mixing when you talk to modern oceanographers. So we actually think that that might be a contribution from terraneous material it's a very deep site. It's hard that the Labrador seawater can get below 4,000 meters in any oceanographic model, so we don't think that's a real oceanographic feature. We think that's more like a lithogenic contribution, which is only specific to that site. There is a lot of work going on about that.
But what about the Nordic seas? Is that still a possibility?
It could be, I mean, without really constraining really well the different composition of the different end members that contribute to the North Atlantic deep water. It's hard to tell, but that's definitely a possibility, yes.
Thank you for the opportunity to present my first result. So I talk about the temperature estimate from a relative new method called clamped isotope. I apply this method to foraminifera at Mount Albano Unico section, which record the mid-Pleistocene transition. So it's Sorry. So the mid-Pleistocene transition, it's marked by a shift of glacial interglacial periods from 41 kiloyears to 100 kiloyears. And we also observe a progressive increase in the amplitude of the climate oscillation. So when we look the orbital parameters, there are no change in the periodicity of the orbital parameters, but the climate variability shows some changes. So there are non-linear response of the climate oscillation to the orbital parameters. That means we have to understand what is the registration of this delta weighting in carbonate values. So like it was present in the past talk, the delta weighting of carbonate register two parameters, the temperature and the delta weighting of the seawater, which will present the variation of the ice sheet. So for the reconstruction of the temperature, I use clamped isotope paleo-thermometer applied to carbonate. So carbonate with a CaCO3, and in the CO3 ion, they will have some exchange, isotopic exchange, like on this equation. This equation depends on the equilibrium constant K, which is only function of the temperatures. And in function of the temperature, you could have some excess of this kind of isotopic assemblage with 2 AV isotope. So to analyze the carbonate, we dissolve it in CO2 and analyze on the mass spectrometers to measure the values of delta 47, which correspond to the excess abundance of the mass 47 isotopologue, which is the CO2 molecules with 2 AV isotopes, so C13, O18, O16. And we will compare this excess abundance to a stochastic distribution of the isotope. So the value of delta 47 is, it only depends on the temperatures. So like I said, this method is relatively new, so we have still a lot of problem with some issue and some problem and some issue. So for example, the quantity of material that we need to have a temperature from delta 47. So for a sample with a minimum of 4 replicate to have a statistical significant temperature, I have to pick 20 milligrams of foraminifera. So for a planktonic foraminifera, foraminifera, it's less than 2 micrograms. So for 20 milligrams, I have to pick around 2,500 foraminifera. So then we have to clean the carbonate. So there are 2 different cleaning protocols. So we decide to use Gruel et al. 2030. And we have also some issue with the calibration to the inter-laboratory comparison. So for that, we have to use an internal calibration. So we perform one on the synthetic calcite. So the paper is in preparation. So with this calibration, we can apply to the mid-Pleistocene transition. So we decide to work on the Montalbano Ionico section, which is located in the south of Italy, close to the Bay of Taranto. There are three advantages to work on this section. So first one, it's a paleomarine continental section. So you have easier access than the logistic we need with oceanographic ship. So the second advantage is through this access, we can bring an unlimited quantity of materials. So for all of my sample, around 5 kilograms of sediment. And the last advantage is the presence of tephra layers, like the white line here. So on the log plot here, you can see we have 9 tephra layers and 3 subpropel layers. So we have a good chronology in this section. I plot here the delta 018 on Bantic for the Montalbano Ionico section. So you can see we have a continued record of the MPT. So I work on 6 intervals. So isotopic stages 19, 20, 21, 22, 31, and 44. I work on 3 different Bantic species. So Cassidulina, which will be with the triangle, Vigerina with the diamond, and Elphidium crispum on the square. So I plot here the temperature that we obtain. So to obtain just these few points, I had to pick 800 milligrams of foraminifera with a minimum of 4 replicates for each point. I plot the uncertainty at 2 sigma. So we can see with these large uncertainties, we can really compare if we have a vital effect or no, for example. But according to the past study, like Tripachi et al. In 2010 or last month Gast et al., they observe no vital effect with clamped isotope. So it means we can combine the temperature from different species together to obtain only 1 temperature. So it's what I did here. So you have 1 point for each intervals. So we observe for the interglacial periods, we have relatively stable temperatures. But for the interglacial for the glacial periods, we have because of these large uncertainties, we couldn't see a strong variation on the younger part of this section, but we observe a colder temperature on the older part of this section, so isotopic stage is 44. Italy, it's a very active tectonic area, so we would like to be sure that we can really compare these temperatures, because maybe they could have an effect of the tectonic on the paleo depths. So for that, I did delta 018 measurement on benthic and planktonic foraminifera, and then I have to say that after, sorry. So we have here the paleo depths based on the host record, but only for the isotopic stages 19, 20, and 21. So we see that for the glacial and interglacial period, we have just a few meters of difference, but we are on the shallow water depths. And we also know that on literature, there are a tectonic event at 0.9 million years. So maybe the water depths could be more larger, and we could be on different water mass. So we would like to know what is the effect on the water depths, and for that I did delta 018 measurement on benthic and planktonic foraminifera to compare the difference through the MPT. So I just cut the plot because it was too long. So this is the delta 018, the temperature from delta 47, and here the delta 018 measurement. So for benthic and planktonic foraminifera, I use Jeanne Record I didn't have enough material to do delta 47 measurement, so I only have enough material for delta 018 measurement. So you can see here for the interglacial periods, we have the same difference between planktonic and benthic foraminiferal. And it's the same for the glacial periods. So that means, that suggests we have an identical structure of the White-short column through the MPT for the interglacial periods and for the glacial periods. So at least we can compare the interglacial temperature together and the glacial temperature together. So the next point is to try to see if it's normal to have a colder temperature on the older part than the younger part of this section. So for that, we compare to another proxy of temperature, so MGCA. So I plot here the temperature from MGCA using UV-Jeanne Peregrina and the calibration from Elderfield et al. 2010. So the first observation is we have systematically higher temperature from the MGCA than from the delta 47. But the other information is that we have the same difference between the glacial and the interglacial periods with the both proxy, with exactly the same difference between the both temperature. So we have to complete with the glacial temperature at the early, at the younger part of the section. So the work is in progress. So to summarize, at the MPT at Montalbano Ionico, we have stable interglacial temperatures. We have a glacial warmer up, so maybe it could be due to a local effect. So to resolve all of your problem, we have to add more replicate to reduce the uncertainties. And we also need to add other glacial and interglacial interval temperatures. But the comparison between the both proxy of temperatures, we don't really understand why we have difference between the both proxy. So I'm working on the new calibration based on foraminifera for clamp stop. So systematically, I complete with MGCM measurement to compare if there are some difference. Thank you.
Did you consider on Montalbano's Ionico section the strong biturbation or for the not well preserved foraminifera, benthic and plantic, are not really very well preserved, and this could be effect on your measurement.
On the measurement of the
magnesium calcium,
yes,
also on the clamp.
Yes, it's one of the hypotheses. It's because we are very close to the coast, so they could have an input of magnesium also. So that can be the magnesium-calcium ratio of the seawater. So, yeah, we have to test. It's for that we use the calibration to really know if there are a strong difference